Quantum biology, I suspect from that cheer we got at the beginning that all I need to say is QB for this crowd. Is that right? Life. Complex, but quantum? That's what we're here to talk about tonight. And in a moment, we're going to talk to some extraordinary scientists and physicists who, let's just say, have a bit of an anxiety about quantum mechanics. And I think we can help them with that tonight. Let's just give it up, first of all, for the biology here in the room. Clap if you are a biological entity. Good, nice. Now, it didn't sound to me as though everyone clapped. If you're not a biological entity, please clap. Yeah. Hunter College, right? There you go, sure. So with deference to all of these cyborgs in the room, we are, the rest of us anyway, biological creatures, and as such, we share a certain kind of wisdom about how things work and how quirkily things can sometimes work. And while the physicists in this room would have us all believe that quantum mechanics is a little terrifying, it's kind of a tangle of irreconcilable phenomena, goes against Newtonian and relativistic concepts of the universe, waves and particles, insane discontinuities of one kind or another, probability, gods throwing dice, oh my goodness, particles that jump energy levels without warning, a freaky merger of local phenomena and non-local events, where connections between things seem to exist across space and time. How can this be, physicists say all the time. We can help them with this, though, because when quantum mechanics entered the world of physics, it was like this elephant in the room, really. I mean, if the elephant were a neutrino, though, and was invisible, and then visible, and then an elephant sometimes maybe more of a rhinoceros, depending on who or what was looking at it, that's the anxiety of quantum mechanics. And we're going to sort all this out tonight. It's the sort of thing that makes physicists crazy, but as biological creatures, let's hold our hands together. Come on, all of us. Biological entities, hold our hands together and try to reassure the physicists that we understand some of what's going on here. Packets of energy that appear out of nowhere and change everything and then disappear again. We understand this. Jeremy Lin, right? Right? Physicists go insane when things are calculated to be one value and then suddenly turn out to be something totally different. We understand this. We just call it the Facebook IPO, right? Yeah. Or when in the quantum world things defy any level of predictability at all. Watching them more closely in this state, it makes them more likely to deliver really scary surprises. We understand this. We just call it North Korea. Physicists hate it when things seem to behave no known laws of physics, but we see this sort of thing all the time. We understand it. It's Donald Trump's hair, right? I mean, what is going on with that hair, obeying no known laws of physics? Finally, quantum mechanics suggests that objects can act across time and space with no apparent connection. I mentioned this a moment ago, as though they're a part of some vast secret conspiracy. Now, why is that so hard to understand? I mean, we've understood for centuries the secret conspiracies that control all of us, right? In God we trust? Yeah, I believe that. Sure. So, together as biological entities, we have a sense, an intuitive sense of the quirkiness of the universe. And in this fusion of biology and quantum mechanics, you may have more knowledge than you think. Of course, there are some of you here, the QBs in the audience, who will laugh at all the right points and will nod when some of the physicists get a little mysterious here. Just turn to them and say, what's going on? Or perhaps I can help you with that. All right, tonight, let's look at the examples of life and biology that we kind of grew up with. And we're going to leave this here as a bit of an example for what we're going to be talking about tonight. We are taught in our science classes that, life is a complicated system of chemical molecules and atoms and interactions between phenomena that become very, very complex and beautiful, but always orderly. Yet, what we're going to learn tonight is that because of quantum mechanics, some of these little balls can detach and disappear and do things unpredictably, and that in fact, animals and biological systems take advantage of the ability to disappear, to be in two places at once, to be doing two things at once. In fact, these orderly molecules can sometimes look like Donald Trump's hair. all right? And that's what we're going to explore tonight. And we're going to do it in very concrete ways with phenomena that you can relate to. For instance, it's not well known why birds are able to navigate and go from one place in the world to the other, because they can't see perfectly all the time, and they don't have radar, at least that we've been able to detect. But what do they have? What is it that's going on in their complicated brain cells that allows them to navigate? We're going to explore that tonight because there may be a quantum explanation of all that. And then, of course, on a much more basic level, the mystery and ubiquity of something called photosynthesis. It's why life is here. Photosynthesis, how plants take light and turn it into energy. Now, we're taught that that's understood, but in fact, it's not so well understood as your science teacher may have led you to believe. And a quantum explanation for photosynthesis is one of the most exciting things happening now in either biology or physics. So, this is going to be a wild ride. Get ready. Here we go. Quantum biology, folks. Let us now welcome to the stage the first person to develop a realizable model for quantum computation. A friend of the World Science Festival, his research focuses on the quantum mechanics of living systems, economics, and cosmology. When he first heard about quantum biology, he thought it was crazy, but now he's hooked. Please welcome MIT professor Seth Lloyd. Next up, a professor of physics at the University of California, Irvine, who believes the biological sciences are currently undergoing a revolution. As more information is gathered about those processes, today he is working to understand quantum entanglement in live birds. Help me welcome Thorsten Ritz. And a dear friend of the World Science Festival, a big star in my life. And finally, our last participant runs a think tank that tackles the big questions of existence. He's wondered how black holes radiate energy, what caused the ripples in the Big Bang afterglow, and now the role of quantum mechanics in the formation of life. Welcome from Arizona State University, Paul Davies. So to all three of you, a lot of what we talk about at the World Science Festival and in some of these edgier topics is a convergence that seems to be taking place between certain fields and other fields. Explain how you see a convergence between biology and quantum mechanics in general terms. Paul?
Right. Well, life is made out of atoms. Atoms behave quantum mechanically. And one thing we need to dispel right at the outset is your little model here. Ball and stick models, for most purposes in biology, seem to be adequate. When we're talking about quantum biology, it's true that the balls and the sticks, that is that the shapes and chemical affinities of the molecules requires quantum mechanics, but we're after something else. We're after all that sort of creepy, weird stuff like tunneling and entanglement and so on, playing a role in biology. Why should that be so? Well, I think one answer is that life has been around for a long time, 3.5 billion years on this planet, at least, and there's plenty of time to learn some quantum trickery if it confers an advantage.
When you say quantum trickery, you're distinguishing between quantum phenomena in the little balls and then organism taking advantage of quantum phenomena to get an advantage in the biological competition.
Right. So supposing some of this weird stuff that we're going to talk about confers an advantage, it doesn't have to be huge, maybe a factor of 2 or even 50% in the speed of some reaction or some more efficient process, then it's no surprise that biology will have selected for that after such a long period of trial and error. So that's one argument. And then the other is that, of course, we can always think about life's origin. Life came out of some sort of molecular milieu, we don't know what it was, that was quantum mechanical, and maybe it's retained some of its quantum origins. That's more speculative.
That something from nothing business is always a sign that there may be some quantum explanation, that's for sure, and we'll come back to that. Seth Lloyd, I said at the top that you thought that quantum biology, when you first heard about it, was crazy, yet it seems to me in science this is a continuing narrative. We have undecidability in mathematics, incompleteness in mathematics. It seems to me a lot of systems contain this sort of internal weirdness, and maybe we need to get used to the fact that this is how the world works. How do you see this convergence between quantum mechanics and biology?
Yeah, well, as you say, John, quantum mechanics is weird. That's kind of its defining characteristic. It's funky and strange, and you have particles behave like waves, and waves behave like particles. So each wave of light that's hitting me right now consists of gajillions of little tiny, that's a technical term too, gajillions of little...
Gajillions, yeah.
Gajillions, yeah. Like
MIT, see.
right, exactly.
Penetrable jargon.
Gajillions of little particles called photons. And the light behaves like waves, but the photons behave like particles, and they're intrinsically quantum mechanical. And, quantum mechanics is weird and strange to us, but say photosynthetic organisms don't really care about that. All they care, as Paul was saying, is, if you can do a little extra quantum hanky-panky, can you reproduce more efficiently? Well, if you can, then quantum hanky-panky is what it's going to be. Weird and strange and counterintuitive or not.
And that's what we're here to talk about. Now, Thorsten Ritz, one of the advantages that quantum mechanics may confer is that it seems to defy our notions of distance, and it seems to defy our notions of time, so that if you use certain quantum mechanic phenomena, you can cheat time and cheat distance. How does that happen in a general way without necessarily referring to some of the things like birds and photosynthesis we're going to talk about a little later?
Well, I think it has a lot to do with what Seth alluded to, that you have these dualities all the time. You have something that is a wave and a particle at the same time, and so once you start asking things like where is it actually placed, it becomes a bit difficult, and you can't answer it in this particular manner anymore. When you think about transport, getting from A to B, there may be something that is in A and B at the same time, and then at some point it just decides to magically go and fall onto one. And there are options that you have in quantum mechanics that you don't have classically. They're sometimes a bit subtle to actually understand what the differences are. But
when you say options, what do you mean? You have options in quantum mechanics that you don't have in classical. What does that mean?
It means that you can have different kinds of behaviors. Classically, you would think that something hops from A to B, and that's, for example, one option. Quantum mechanically, you can have something that stays in both things at the same time, while you're also moving things around. So you have it's this wave-like nature that is something that's a concept that is far spread, but at the same time, it's a particle which you put on a given location.
In my deference to Richard Feynman, or possibly to the humanists here in the Hunter College audience, is this a product of our observation? In other words, is this how we perceive it, or is it really in both places at the same time, or is that one of the unresolvable issues? Thorsten. Sorry. Let's just forget that. Is there a God? Is there a God?
I'll ask him that. I heard that once God saw quantum mechanics, he smiled, and so that.
She.
Very good.
Oh, she, yeah.
But it's
Go ahead,
it's
Paul.
the word really that let you down there, because reality, the nature of reality in quantum mechanics is not like in everyday life. And to say, is it really in two places at once, or was it really there, or is it really moving with such and such? If you believe in standard quantum mechanics, you simply can't answer questions like that. So your question was actually meaningless.
Great.
But well done.
That's metaphysics for you. Don't you love that? So let's take that a little further down the road. Part of one of these features of quantum mechanical phenomena is that they are rarely observable, relatively rarely observable. Now, often the explanation is because it happens at such a tiny scale, but there are other reasons why quantum phenomena aren't observable, and it relates to the complexity or the noise of the system. Explain what that's about.
Right. So Seth already explained that photons can be like waves or particles, so can electrons, and the key factor in quantum mechanics is this wave-like nature. If you want to retain the quantum features, not all of them, but most of them, you've got to keep that wave-like nature undisturbed. And let me just give you a simple example. Imagine that you go to a flat pond, you drop a couple of stones simultaneously, splash, the ripples spread out, and then what you find is that the waves from one start overlapping the waves from the other. Now, in some places, the waves will add together, and in some places, they'll cancel. So that's called coherence. Now, if you came along with a stick and just sort of jiggled the water like that, it would mess all that up. You'd lose that pattern. So it's essential in quantum mechanics that you retain this coherence if you want to see in a simple way quantum effects at work. Quantum effects may still be there, but if it's all messed up, if it's decohered, it's also lost in the detail.
All right, so coherence refers to a state where, like the smooth pond, you can see the actions of the individual stones being tossed in.
The waves, the phases, or whether the waves are in step or out of step, that aspect is retained and not disturbed.
And decoherence refers to attempting to skip stones in the middle of a thunderstorm in the same pond.
Right, it's all messed up because there's external interference. And in the case of, say, electrons, that external interference might be the surrounding environment that's coupling to it. And so guys like Seth that try to actually utilize, make quantum technology, have to screen out all that environment. And that's the tricky thing with biology, because it doesn't look like a very screened environment. It's sort of warm and wet, and what you really want is something close to absolute zero of temperature, shielded from all that disturbing environmental influence.
So it's a little like in a quiet room when somebody's cell phone goes off, you can really hear it.
Won't be mine.
But if you're on the subway,
off.
you can't. That's a decohering environment. A coherent environment is the quiet room, right?
Right.
I just thought of that. It just kind of randomly occurred to me there.
Which is why, by the way, it was so surprising when the first evidence came out that quantum mechanics was playing a strong role in biological systems, because cells are hot, wet places with all kinds of noise and stuff going along. When we build quantum computers, we try to put everything down at very, very low temperature. So, you have electron that's here and there at the same time, right? And its wave is waving in this coherent fashion. And if there's any kind of jiggling around, then it starts, getting all decoherent, as Paul was saying. And once it's decoherent, then it could just as well be here or there at the same time. It's no longer here and there at the same time. And nobody expected that in biological systems in cells, you could have things like particles of light or particles of energy that are like, coherently going like this, because cells are a hostile environment to quantum coherence.
At least theoretically. It
Well,
looks like they are.
Yeah, well, I mean, theoretically, people thought, this will never happen, with the exception, of course, of Roger Penrose, but let's not talk about that.
Okay. Yeah. All right. How many of you are familiar with quantum computing, something that Seth just talked about? Just clap. Yeah, okay. All right. So there's a good understanding of quantum computing. Is part of the journey that we're going to take tonight, Thorsten, an attempt to figure out if the phenomena that Seth is talking about, basically taking a system and reducing it to a kind of coherent state where you can take advantage in information terms of quantum interactions that potentially cheat time and cheat spatial coherence, that sort of thing, that biological systems are also creating states where they can do their own quantum computing. Is that kind of what we're talking about here?
I would hope that actually the arrow goes both ways, that we learn from biology potentially something about how to create such states in hot and wet environments. And there may be different ideas. I mean, obviously, nature doesn't cool us down to 200 degrees minus or something like that. And it has, if it works there, it has figured out how to work there. And then the other way around, I think that from understanding how to actually control the quantum computer, you can have some good ideas of what you should look for in biological systems, how you can probe them, and how you can manipulate them in ways that you haven't thought about before. And that's actually how you might test whether something like that is actually going on. So I really hope it's going both ways.
Paul, since we're talking about you can't cool things down to 200 degrees Kelvin or whatever.
Well, you can, but you'd be dead.
Yeah. I studied in science class, actually, so I did know that. But thank you so much. And what sorts of states in biological systems might be eligible for having little pockets of coherence where you could take advantage of quantum, without too much preempting what we're going to be talking about in a few minutes?
Right. So I think the great hope is that there can be screening effects, natural screening effects, and this might be because the way the systems couple to their environment might be mismatched in some way, that we're not talking about long periods of time. You see, what the quantum computer industry would like is to have something that remains coherent, I don't know, Seth, you'll have to tell me, but over seconds or minutes or, however long you're going to take to do the calculation. Nobody, I think, is suggesting in biology that it's any more than, well, it might just be like picoseconds, trillionth of a second, maybe a bit longer, but but still pretty brief by human standards.
But if we're trying to,
but nevertheless, if you can keep this stuff at bay for long enough to do something useful, it could be biochemically significant.
So the way to think about this, and again, I propagate errors whenever I speak up here, but the way to think about this is not unlike, say, the mitochondria in a cell is a little organ that does very specialized things. It happens to be an energy producer, a little bit of an engine. In this case, there may be in cells quantum organs that contain these screening mechanisms, even for a few picoseconds, that allow the cell to figure out if something's doing this or that and make a decision based on that. Is that kind of...
Right, yeah, and because we don't know what this screening
Right.
mechanism is, it might have something to do with water. You know, water that comes out of the tap in your bathroom is completely different from the water inside the cells, because water is a polar molecule and the way it lines up around organic molecules and so on. It may well be that has some sort of screening effect. It's not well understood. And it could be...
So let's just... The water is completely different because the individual water molecules in a biological system...
become ordered.
They're
They're ordered. You know, they're not just chaotic. They can
little
order
magnetic...
themselves, and the way they cluster around organic molecules and so on. It's a very complex subject, only partially understood. But that, for example, could play an important role. We don't know. And I think the big question that we'd all like answered is, we're going to be talking about some specific cases where it looks like quantum mechanics might play a role in biology. Are these just peaks of a quantum iceberg that is somehow pervasive and is absolutely fundamental to understanding the weirdness of life? Or are they just isolated examples that biology has exploited here and there? And we'll just find a few more of them, and that'll be it. The subject of quantum biology will fill a very small textbook. Well, we don't know. This is a subject struggling to get out.
And one of the things that we love to do here at the World Science Festival is to, I suppose, suggest that what you're seeing here is the cutting edge, that this is absolutely the first time any of this has ever been thought of. But in this particular case, the proposition of quantum biology is not a new one. Do any of you know when it was first proposed and under what circumstances?
Heisenberg, the founders of quantum mechanics, Schrödinger, Heisenberg, Wigner, all these people, they thought, well, here we have a theory that's so powerful, it's explained all of matter in just a few years, so maybe it's got the power to explain life too. And they were convinced that either quantum mechanics or some derivative of it, some post-quantum mechanics, would hold the secret to life. So this is a very old idea, but it really didn't work out in quite the way they envisaged.
Sort of personal question, and you guys interact with other scientists. Why is there all this anxiety about quantum mechanics? You know, you can win a Nobel Prize and you can get up there in your speech and say, I don't buy that quantum stuff, but thanks for the prize. I mean Einstein basically did that. Why all the anxiety?
Well, there's actually, you put your finger on a funny phenomenon, which is that Einstein is not the only person who got his Nobel Prize in quantum mechanics who didn't believe in it. And, but there are contemporary ones. Are they in the audience here? I'm not going to mention their names.
Any Nobels here in the audience?
Yeah, okay. So, and I think it has to do with the following, that quantum mechanics is just intrinsically counterintuitive. And, you know, babies, when they lose their intuition for quantum mechanics when they're about 3 months old, which is the age when they learn to play peekaboo.
Yeah,
right?
we need to get in early.
Right.
Teach them
so I mean, the way that peekaboo, yes. Exactly. I mean, the reason that peekaboo works is that, you know, if you play peekaboo with a kid who is younger than 3 months old, then who here has played peekaboo with little kids here? All right, good. I think there are people.
Wow, there are almost more Nobels in the audience.
What's going on? So if the kid is younger than 3 months old, you play peekaboo with them, and she'll just be like, Daddy left the room. But at 3 months old, you play peekaboo, and she's looking at you like this. You know, you're like that, she's looking at you. She knows you're there, right? That's why it's fun, because when you actually go peekaboo, the fact she knows you're there is confirmed. It makes her happy because she has gained object permanence, a sense of object permanence, which means her intuition for quantum mechanics has been destroyed.
Okay, now there you lost me. I was loving the whole peekaboo thing, but then what do you mean lost the sense for quantum mechanics?
In quantum mechanics, if you can't see me, I'm not there. Right? Things aren't there. You can't say, you know, electrons are here and there at the same time until you look and say, oh, electron is there.
Not really there.
But I thought quantum mechanics was more, if I see you, you still might not be there.
Oh, yeah, well, that too.
Oh. Great. All right. So let's move into a concrete example here. But before we go, all three of you, what are the tools we're going to use to think about quantum phenomena in a biological system, and we'll talk about the first example in a moment. You mentioned the sort of wave-particle ambivalence. You've mentioned the sort of time invariance. Just reiterate that so that we have our toolkit ready when we start thinking about birds.
Okay, so the sort of things that we're talking about is not quantum mechanics explaining why the sizes and shapes of molecules are what they are. It's things like coherence, so imagine the waves sort of all in step and not being too disturbed. Tunneling, and tunneling means imagine you throw a ball at a window, then it'll either bounce back or it'll shatter the window. But imagine if you throw a ball at the window and it appears on the other side of the window without breaking it. It's called tunneling. That happens a lot in
or really good luck.
With quantum particles. Yeah. And then there's this other thing we call entanglement, which is sort of what Einstein called spooky action at a distance, where you might have two particles a long way apart, sort of know what each other is doing, even though neither knows what it's. Let's put it this way: it's a good, right. Correlation without causation. So what's happening here and what's happening there are linked in a way that's impossible to explain in terms of any sort of everyday type of reality.
Well, but to be really precise, it's two particles that must have some connection, even though there is no physical connection and they're in no sort of force arrangement. They're not in a magnetic field or any sort of way. Right. So you can't explain it through traditional forces.
Right. That's
Thorsten, would you
Yeah,
add
because
that?
it happens at exactly the same point, right? I mean, normally you expect that if you measure something over here, you finally look at the thing on the one side. What is it? Are you, an electron? Are you, what are you? That then it takes a certain amount of time to have that information travel to the other one. But when you actually look at that, you'll find that at the same time, the decisions are made.
But they're not signaling faster than light. That's really important.
Yeah, and so that's.
All right, well, Seth, and I have a question for you as we get into the concrete example here. As you talk about this, it occurs to me, you guys watch Nova, right? Or National Geographic specials, any of that stuff? Right, okay. You don't? They cancel their cable, all these folks out here. So you often say, if you see a show about a shark, okay, they'll talk about how, sharks can sense blood 3 continents away. Okay, so when the blood enters the water, they're already smelling it. And somehow there's a kind of an explanation at the end of that paragraph where they say, and it's because there's like billions of parts per million, and it's like they're really, really sensitive nose, and so they can smell it much better than you, kind of thing. Right? Now, I'm not buying it, okay? Is it possible that this extremely sensitive smell of some organisms might have a quantum dimension, Seth?
Yeah, so of the phenomena that are thought to have some connection of quantum mechanics, for which there is actual evidence, one of them is actually the sense of smell. The old theory of the sense of smell, which was put forward by Linus Pauling in the 1940s, is it's a lock and key mechanism. You get a molecule, it's got some shape, there's a receptor inside your nose, the molecule comes in, fits into the receptor, and if it fits into the receptor, boop, neural signal comes out, and you smell it.
So one of these has to get in my nose.
Yeah, well, let's, better yours than mine.
I'm not going to try it. Don't try it at home.
Yeah, that looks a little big, actually.
Yeah.
In fact, one of the pieces of evidence for this is that molecules that are larger than musk, which are the smelly, very smelly, large molecules, if they're bigger, you can't smell them because they won't even lock in the receptors. So I think those guys are out. We'll all be happy about that. But then there's a funny thing that happens, which is you'll have a molecule that looks exactly the same as the other one, but there's a little piece over here that's slightly different. Like one of the hydrogens has been replaced by deuterium, heavy hydrogen, which weighs twice as much. But chemically, it's identical. It's going to fit in exactly the same receptor. And yet, it smells almost entirely different. My friend Luca Turin, who works on this theory, he's an expert on perfume. He wrote a great book called Perfume. And the best part are the descriptions of the bad perfumes, like, slutty. No, slutty is too good for this perfume. Right, so we
got hanky panky from you, slutty, hot, wet.
I know. I'm sorry. My mind works in that way.
Family show here, bud. Right.
And you were describing entanglement as something.
That's true. Yes.
Well, never. I won't go down that.
I think we need to get a grip on ourselves.
Let's not talk about how that. So this, how Lucas says, he says, well, you know, this molecule, the first one, say the organic one found in nature has a grassy, sharp, slightly sweet smell like a fine Marlborough Sauvignon Blanc. Whereas the one that has the slightly different thing, which presumably is sitting with the same receptor, smells like rotten eggs. So how can this be? They're locking in the same receptors. So the theory is that even if the shape of the molecule is the same, so it locks in the same receptors, because it's got this slight difference, where this piece is heavier, this deuterium is twice as heavy as ordinary hydrogen, it vibrates in a different fashion. So the hydrogen bond is vibrating like this, but the deuterium bond is vibrating like this. And this kind of wave-like nature is a peculiarly quantum kind of effect. And somehow this receptor is able to sense this vibrational difference by absorbing a single quantum of sound, a vibrational quantum from the molecule. You could think of it as like the quantum of smell.
Is it like a billiard table filled with balls, and instead of one ball traversing the table to interact with another particle, it's actually passing something through the crowd, and that is what you're sensing? No isn't acceptable.
It's more like what Paul.
No,
it's more like what Paul talked about this ball that you throw through a window, and you know it goes through this tunneling effect. Now you can imagine if there was something that's vibrating in that window, it may be easier or harder to go have that ball fall through. And so in a similar way, this vibration that you have in there might help something tunnel or not tunnel, and that may give you the signal. That's the idea of this mechanism.
All right, let's take a look at one of the most extraordinary mysteries in the biological world, and it's something that we can observe every day, and it's the migration of birds. There are birds that traverse the globe and return to very, very specific places at very, very specific times and have to navigate in a way that's even more complicated than what airplanes have to do. And there are a lot of explanations for this, but no one's really solved the puzzle, and it turns out that this phenomenon right here that we're observing is on the cutting edge of this interaction of quantum mechanics and biology. Thorsten, would you care to take a look at this? What's going on?
I'm looking at it. Well, we're seeing here two geese that are migrating, I hope. I don't know, they're flying. So, and the amazing thing is they don't just go back generally to the area they came from. They go back to the same spot. So they move thousands of miles, and then they go back to the same spot. They do that without a GPS, as far as we can tell. And they do that with bird brains that we generally don't think about as particularly intelligent.
Now, when you say they do it without a GPS, it means they're not interacting with some database that would reside on a satellite or interacting with some other appliance that would deliver in real time information to them on where they are in space. They've got to doing it some other.
We don't
yeah,
know that.
So the GPS is really sort of cheating nowadays with navigation because we have the satellite and gives us our position and so on. This is really talking about navigating with a map and a compass. And so in the old school way, if you're hiking and then you have a map and you move things around, that's really what we think they have. And one of the compasses, they have multiple compasses, but one of the compasses is a magnetic compass that they possess. And that's actually, it's an interesting story how that was found out. It was in the 1850s, so there was a scientist who just sort of wrote this in almost poetic language. Maybe even birds have this compass that allows them to find their ways. And then people in the 1930s tried to glue magnets on birds to see whether you can confuse them. And that was very inconclusive in the end of the day. And it was only in the late 1960s, early 1970s that Wolfgang Wiltschko actually made the definitive experiment that we now all believe is true. And he was actually studying whether a bird in a little cage would behave the same way as if it's flying. If you take that goose and put it in a cage, maybe you use a smaller bird to make your life easier, would it also go north and south in the respective seasons? And he found yes, but he also noticed that some birds in metal cages behave differently. And so then he started to look at magnetic effects. And what he found is that if he turns the magnetic field, what you can easily do, so that magnetic north points, let's say, to east, these birds would go east instead of north. And so he could turn them whichever way he wanted. And so that's a very beautiful lab experiment that had been done in the early 70s, has been reproduced many times.
But it's one of those experiments that solve something, but actually suggests a much greater mystery. I mean, there's no compass, and the mechanism for how the bird might be detecting north, south, east, or west, either neurologically or in some even more mysterious way, is not well understood. What were the experiments and investigations that began to look at some explanations for that?
Well, it's a behavior. So we see clearly that they can detect the magnetic field of the Earth and they can get directional information from it. So that's clear. What we cannot do is to point to an organ and say, this is the magnetic organ. I mean, even if you don't fully understand how the eye works, you know that it's involved in vision. If you don't have it, you can't see. But we can't point and say this is the magnetic organ. So the experiments, we're still in a phase, I want to make very clear, that we don't know how that compass works. So we have various ideas that are out there, and that's where the physics comes in, because it's actually not that easy to detect a magnetic field that is so weak as a geomagnetic field. It took us humans until like 1100 or so to figure that out, so we've been around for quite a while. And
the only way we detected it was with a needle in water on a cork or something like that.
Exactly, like a lodestone, and then you have this mysterious force. So maybe it's a precursor to quantum mechanics. It was weird, and so, yeah. But essentially...
I like it. Go with that.
It's one idea that you have a little compass needle, but that's not the quantum one. The quantum idea is coming from looking at particular chemical reactions where, and that was maybe a concept we should have discussed before, and it's the spin of an electron. So essentially, as a charged particle moves around its own axis, it's a moved charged particle, and that creates a magnetic field. So you can think of a spin in some ways as a little magnetic needle. But unlike a magnetic needle that just turns north and then stays there, when you try to realign a spin, it actually evades that, and it makes this funny movement like a tabletop when you go around. And so imagine you have these tabletops. Normally these electrons like to be in a way that they cancel the effects of each other. That's stuff we learn in high school. But if you rip them apart, you take light and you move one electron to another side, you create a state that suddenly becomes sensitive to magnetic fields because it has this coherent quantum nature. And if you have this particular state for a while, you can actually detect effects of the magnetic field.
So if you could figure out in your bird brain how to, for a few moments, when you needed to detect a magnetic field, how to separate certain particles with spin from their molecular prisons where that spin doesn't really matter, if you could figure out how to do that, you might have your detector.
Yeah, that's an idea. And then if you have that idea that Paul is talking about, that you isolate it, so that you have that prison and it's not totally disrupted and broken into by all kinds of other things that are interacting with this molecule.
So are there any molecules that qualify, any substances found in bird brains that could actually do something like that?
Well, in fact, I mean, this reaction that you absorb light and then transfer an electron is a very basic reaction. It's also the key reaction in photosynthesis, and you can create states like that are magnetically sensitive. Now, the question was, one of the things is, in order to absorb light, you need to have certain kinds of molecules, light absorbers, and they don't exist, there aren't that many around that absorb normal light. And so chlorophylls do it, but we don't think that birds are photosynthetic, and the only molecule that we think of at this moment is called cryptochrome. It's a blue-green light photoreceptor. It's a cryptic chromophore. The name comes because even blind people get jet-lagged. And so the idea was that there needs to be another photoreceptor in humans that tells us there's light out there. And so it was called the cryptic chromophore, the cryptic light absorber. And ironically, it turns out that the cryptochrome that was found is indeed in fruit flies. It tells the day and night rhythm, but not in humans. It ends up being a different molecule. So now it's a complete misnomer, but it's a new molecule that has been discovered in the late 90s, and this is one candidate that we have there.
So cryptochrome does exist in birds?
It does exist in birds, and it exists in interesting places where I would like to have it for a magnetic compass, like the outer segments of ice, where they're well ordered, and so forth.
So in theory, and again, has anyone proved that this is the case, or is this like a interesting supposition?
There's, I would say we have clues. It's not a real proof. So what you ideally would want to do is you take a migratory bird, you take out the cryptochromes, you show that their compass doesn't work anymore. And then you reintroduce the cryptochromes, let's say in these eyes, and then the compass works again. That would be a beautiful experiment, but you can't do it because we technologically just don't have the tools genetically to interact with the birds.
Do we think that the cryptochrome exists in some specific organ that's involved in this compass, or is it part of the photoreceptors that operate the eye in the birds?
We think that this mechanism, this basic idea is that the magnetic field is an indirect effect on light sensing. It could really be an indirect effect on vision, that you modify how the visual receptors act, and whether it is at the very first point or whether you hijack the vision in a later step, that's a detailed question that we can't answer at this point.
So something about the light hitting cryptochrome releases these photons and particles with spin. The bird makes some sort of detection of the magnetic field and then modifies its course accordingly. Paul, does that sound plausible?
Yeah, so it's not photons, it's electrons and ions that form this pair, it's this entangled pair. And then these things are spinning in their different magnetic fields, slightly different because one, they both feel the Earth's field, but the other one feels magnetic fields due to the other particles.
So the photon creates the entangled pair.
It gets sort of out of step. The photon comes in and creates this separated entangled pair. And then if I'm getting this right, when they merge again and release the energy, whether they're sort of in step or out of step depends on how much energy gets released, which will depend on what sort of neurotransmitter is released. So the bird will literally see the magnetic field. I mean, that was
that was the basic idea. And the light is there actually to provide order in the beginning. Light is a lot of energy in a biological system. And so when you know that, if your room is dirty, you need to spend energy to make it clean, right? And that's a basic law. If you want order,
know that? You all know that?
if you want order, you need to spend energy. And light provides a lot of energy. So you can create a state that's very, very ordered in the beginning. And that's really the trick to this. You have something that is extremely ordered, and then it takes time. You know that from your room as well. It takes a while until it gets back to its normal state and gets disordered. And so if you have this reaction going fast enough so that you don't have time through thermal fluctuations and all these movements to disrupt that state, you get a state that's magnetically sensitive. And then there's another trick that you save that state away, so to speak, in a hard drive that then remembers that state. But that's sort of a detailed step in there.
Right. I would say that in my family, my kids' room cleaning is not a quantum effect, it's more glacial.
Maybe you should try the quantum nature and maybe it gets better.
Right. Seth, how do you evaluate the sort of quantum mechanical plausibility of what Thorsten and Paul are talking about?
It's certainly very plausible. And the indirect evidence, for instance, that the birds need green light in order to navigate suggests that somehow these green photons or green or blue photons are supposed to enable this to occur. And it does make sense. It sounded kind of crazy when I first heard about it. That all this, I've got to say that I'm come from a generation who I never studied biology, not even in kindergarten, except mucking around in the mud and stuff like that. So I'm constantly stunned by what happens in biological systems.
Oh, you seem to have a real feel for biology, Seth. And
I
the
am.
Things that you say,
I was one of the people who are biological organisms when you had people clapping at the beginning.
Yeah.
But we don't have direct experimental evidence. But it does make sense, and for the following reason. The thing that we were talking about that is really weird and counterintuitive about having these effects like entanglement or quantum coherence in biological systems is, cells are hot, wet places that are incredibly decohering. And these states that you create, these entangled electron states, where you create an electron that this electron here is spin up and this one's down, but it doesn't matter which way it is, they're always entangled with each other. Entangled states are excruciatingly sensitive to noise. So at first it seems, oh no, it's crazy. They can't possibly, retain their coherence over time in this biological environment. But look what it's actually doing. This entangled state is actually trying to detect something which is a perturbation. They're actually sensitive to the presence of this small magnetic field, which messes up their entanglement. It's actually disturbing the entanglement which ends up getting detected when these electrons try to recombine. If the magnetic field comes up and disturbs their entanglement by a small amount, then they recombine at a different rate. So in fact, it's what looks like to be the bad thing here. That is that there's too much noise, that these states are exquisitely sensitive to this noise. One person's noise may be another person's signal. And in this case, they're using this sensitivity to detect this signal. So it's kind of turning on the head what one normally thinks of in quantum computing as like, oh, decoherence is bad, interactions with the environment are bad. Here, interaction with the environment is good because it's this very sensitive, tiny magnetic field you're trying to detect. So I think it's quite plausible. There's not a kind of like molecular biological smoking gun yet, but I think
But it passes, it seems to me, 3 fundamental tests, and maybe there are more, and just hold on for 1 second, Thorsten. It passes the test of it, in theory, can detect a very, very weak magnetic field, that the perturbation itself, if it's detectable at all, would be within the range of something that biological system could detect, number 1. Number 2, it happens quickly enough so that it could be useful in the flying times of a bird in ways that you would need for navigation. And the qualities of the cryptochrome molecule, in theory, create this kind of screening mechanism for allowing coherence to occur long enough for the detection to take place. Those 3 tests are passed by this, right?
yeah, it smells like a quantum, it quacks like a quantum, it's a quantum.
All right.
But
Thorsten?
there's another test as well with, with the radio frequency fields.
Right.
The resonance.
So from a physical point, and that was actually why I entered that field. I mean, this idea was proposed by Klaus Schulten also in the 70s. And when I looked at that study, there was nothing in there that made that impossible from a physics point. It all checked out. But biologists had completely overlooked it because it was published in an obscure solid-state physics journal with a German title. So no biologist in their own right would ever read this. And even if they did, they wouldn't understand it because it was written in the language of physical chemistry. So we know a bit more than that. So I told you that with birds, we can't do this experiment. But with fruit flies and other organisms, you can actually take out the cryptochromes, put them back in. And you see that their magnetic sensitivity gets affected. It goes away when you take away the cryptochromes. You put them back in. It works again. And even the cool thing, you put the human cryptochromes in there, and you recover their ability. Then there's another test that we devised. And if you can't take a bird and kill it and look at it, the next thing you do, you try to confuse it. So if you believe that they have little compass needles, one of the things you can do is you give a strong magnetic pulse to remagnetize it. Like when you have a compass needle, right, you can put a strong magnet, you can remagnetize it, and try to have them go south. So that's if you believe in that idea. Now, if you believe in the quantum idea, one of the things you can do is you can create artificial magnetic fields that flip spins around. And these are oscillating fields of frequencies in the megahertz range, so that frequent, low radio frequency fields. And as you apply them, these birds get confused in a pattern that matches very well the expectations from such a mechanism. So, for example, that oscillating field needs to be perpendicular to the static field to have an effect. If you go to an MRI, it's the same idea. There's a strong magnetic field, and then there's an oscillating field that probes in this case, the nuclear spins, not the electron spins. And so you do this experiment with the bird, you have the oscillating field perpendicular, they get confused, you take that exactly same field, you make it parallel, it's as if the field wasn't present. And so these are some of the signatures you would really expect. And that's very good. It's not direct evidence, but it's indirect evidence that really makes this more than just a plausibility, but something where there's really some support.
And so if I come up here to these, and if anyone can guess what this molecule is, you win the Lexus. So the question of whether there is a perpendicular or orthogonality or whatever you want to call it, a perpendicular or parallel element here, can be measured directly in the configuration of the molecule, so you can figure out if the box is there for the quantum phenomenon just by looking at the molecule, right, Paul?
Well, you've got to have it, the molecule's got to be correctly oriented. You can't have them just jiggling around. So the idea is that in the eye of the bird, it has a fixed orientation. Otherwise, none of this would make any sense. Correct?
But that's
Yes.
what biological systems do. They order molecules, right? They put them in interesting.
And that is why
specialized
I would like to see them in the outer segments of photoreceptor cells, where you not only have ordered molecules, but you have ordered membranes that are beautifully stacked, hundreds and thousands of them. And so that would be a logical place for something like that to take place.
How do you see, Paul, the idea that this phenomenon that we're talking about of these birds is an example of evolution capturing a quantum phenomenon and using it for some sort of competitive advantage in the environment?
Right, so it leads inevitably to the question, well, if birds can do it, why can't people do it? In fact, I used to work with a man who claimed he could detect magnetic north when blindfolded. I never did any experiments, but I suppose it's not inconceivable that it's pervasive throughout biology. I don't know, but I suspect it is just restricted to birds. So this is what we'd like to know. Is it just here and there? There's a little bit of quantum trickery that is going to give the organism the evolutionary edge, Or is there something much more pervasive? And the problem is, it comes right down to this, this word that we always run into, complexity. Biological organisms are incredibly complex. Now, the way you've been presenting this is that quantum mechanics is really hard to understand, deeply mysterious and so on, but life is something very familiar. But for us, it's around the other way. You know, we understand quantum mechanics, that's no problem, but we don't understand life. You know, because life is so incredibly complex. Life, to a physicist, life looks just like magic. It really does. It's really hard to understand what's going on. And so the thing is that if quantum mechanics is playing a really deep role in life, it's obscured because of that complexity. If you just take something, there's one particular molecule that I like, the polymerase motor. So this is the molecule that is relatively small, biologically speaking, but still a huge number of atoms, impossible for a theoretical physicist to describe, bolts itself onto the DNA, the unzipped DNA, and it sort of rivets all the base pairs. So it's sucking in the nucleotides and then making all the right rivets. And it chugs along at about 100 base pairs a second. It's like a little motor. And it turns out if you tension the DNA, it slows down and then can actually go into reverse. So here's something you think an engineer or a physicist could wrap his or her head around, because it's a, you know, it's a little machine that's doing a job with well-defined properties in terms of speed and so on.
So you look at DNA and you go, magic, but then you see it like building and you go, I saw that happening in downtown when they were building the World Trade Center.
So the question we'd like to know is,
an engineering
is this all about just ball and stick stuff, too complicated, or is there some quantum goings-on inside this little motor? Well, how can we tell? It is so incredibly complex. But it could well be that such fundamental processes as DNA replication, or even DNA information processing, though that's a bit more of a stretch, might be fundamentally quantum mechanical. And that would be a whole new level. Then quantum biology would really take off. We can't get at it at the moment because of this stupendous complexity.
But in general, when you're looking at processes that are molecular, even though they're life-based, are orderly and have to rely on well-known physical and chemical properties of atoms to maintain the orderliness of either the assembly or the disassembly of whatever process you're talking about, that's a candidate for looking at quantum phenomena.
Right, I mean the dependability of nature, so that the fact that we have molecules with shapes and so on like that is also quantum mechanical. But what we'd like to know is whether things like the tunneling or the entanglement are playing a role as well. And I'm sure they are playing, you know, it's more than just the examples we've done. There must be other examples. But what Schrödinger and company really wanted was that quantum mechanics somehow would be the essence of life. That, you know, like the weird aspects of life would be fundamentally quantum in their nature, so that one day we will finally, through quantum mechanics, say, oh, now we know why life does all this sort of magical stuff. We're a long way from that, and it may be that that's simply misconceived.
Although that refers, you know, as close to anything as we've said tonight, to some of the kind of folksy anxieties and notions of quirkiness that exist sort of in everyday psychological and biological life. You're suggesting that Schrödinger and Wigner and that gang, that part of their temperance about being perhaps initially repelled by quantum mechanics was almost a humanistic impulse to say, this is weird, what else do I know that's weird? Well, life is weird.
Right.
And they saw a unity there almost immediately back in the 1930s.
Life is clearly a distinctive state of matter. We don't know of anything else like it. We separate the living world from the non-living world. Now, there's got to be some transition between the two, because life began somehow. We don't know how. Maybe quantum mechanics played a role there. But it is very, very distinctive in its properties. And so we would like to know, is that distinctiveness fundamentally quantum mechanical, or is it just the complexity?
All right, we'll talk
and you know, I'd love to say it's quantum mechanical. I'm not going to hold my hand on my heart and say it is. But a little part of my mind is open to the fact that one day we may understand it. And it may even be that we need to extend quantum mechanics, because I think Schrödinger and his colleagues felt that quantum mechanics wasn't the final theory of matter, that there would be some post-quantum mechanics that would replace it, that would explain life and, you know, maybe even consciousness, but let's not go there.
Or even that it's a window to something that is fundamentally... Well, let's hold that for a moment. By the way, I'm a particle when I'm on this side of the stage. I'm a wave when I'm over there. How are we doing in terms of understanding here? Everybody feeling pretty good? Yeah? All right, good. So let's move on to another concrete example of where we think quantum phenomena is really driving life. And of course, this is the mother lode of all life forces, the question of how leaves of plants take sunlight and photons and convert it into energy. I mean, this is something that we're taught, happens in a kind of an ATP sort of chain. I remember doing the kind of ball and stick diagrams of how photosynthesis works. But when you got to the part about the light comes in and then energy happens and then the plant grows, you know, it seemed to me there was a couple of pieces missing. Is that really the case with photosynthesis? Is it a mystery that at a certain level is not fully understood, or are we rethinking photosynthesis when we look at quantum phenomena? Seth?
So this is how I got involved in this subject, because until 5 years ago, I didn't know anything about photosynthesis or really about biology. And then one morning I woke up and I read in the New York Times that green sulfur bacteria were performing quantum computations. And this, like, I and my colleagues doing quantum computing, we burst into hysterical laughter. What kind of, you know, crackpot people would say this kind of thing? That's crazy. But then I went and read the article, and the article was from this, the Fleming group at Oxford, were the very fine and amazing and really serious scientists. And so I said, well, you know, I better figure out what the heck is going on there. And so I went and started reading it, and it really, the evidence, which is very strong, and I would say that the evidence for quantum mechanics playing a role in photosynthesis is the one where we have the most direct experimental evidence, basically from zapping bacteria with lasers and seeing what happens, right? You know, hey, that's how science works, right?
They don't mind.
Well, there's no Society for Prevention of Cruelty to Bacteria yet.
At Hunter, there might be.
Yeah. So the way that, in my crude physicist understanding of photosynthesis, what happens is a particle of light, a photon, it has a lot of energy, comes in and it hits a leaf or a green bacteria. Now, if the photon is green, so if it's vibrating at the color green, then it gets reflected off, which is why the stuff appears green, because it's like reflecting off green photons. On the other hand, if it's the color of your shirt, this beautiful, may I say, that's a very nice shirt that you have.
Oh,
so, but
thank you, Seth. We'll have you back.
This beautiful purple color. Now, purple is a color that green plants love to absorb. So this purple photon is going to come in, and it's absorbed by a chlorophyll molecule in the plant. The chlorophyll molecule is like a little box where energy can exist. And what happens is the photon comes in and it creates an electron hole pair. So it separates an electron from where it is. The electron jumps, as we were describing before. This is what happens in photosynthesis when light interacts with matters. It excites an electron. And in fact, this quantum particle that you have, this electron hole pair, is called an exciton. Because, you know, photon is a particle of light, phonon is a particle of sound, a moron, no, that's a particle of stupidity. Exciton is a particle of excitement or energy. And this exciton then hops from chlorophyll molecule to chlorophyll molecule for hundreds of thousands of chlorophyll molecules till it gets to a place called the reaction center, which is a special place where this energy in the exciton can be turned into chemical energy and make stuff like more plants or more bacteria. And for many years, this process was thought to be very mysterious because, in fact, this transport process is extremely efficient, almost 100% efficient.
All right, so the fact that it's 100% efficient means that the metaphor could not be something to do with billiard balls, because you'd lose energy as you moved across the table and bumped into other balls. And even though you might transfer some energy, you would lose enough so that very, very quickly you'd have zero energy by the time you got to the reaction site.
Right, and of course, you know, having zero energy when you get to the reaction center is not good for things that are evolving and wanting to have baby bacteria and baby plants and stuff like that.
So you had to create a transfer mechanism for photosynthesis to work at the efficiency that we've observed that it works, a transfer mechanism that loses almost nothing from the encounter with photons and the encounter with the reaction center.
Right. And it turns out that the way that this happens is intrinsically very quantum mechanical. And it's hard to understand how this process can be so efficient, this energy transfer process, if this exciton, as it hops from chlorophyll molecule to chlorophyll molecule, is just taking one kind of random-looking path through this gigantic complex. I mean, it's gigantic in the sense that it's like many, 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 many atoms. It's not, you can't see it with the naked eye, but it's gigantic from the atomic
I know,
level.
you're just learning biology.
Yeah, I understand, right, that's right. It's humongous, it's gigantic.
Yeah.
So these guys at Berkeley were essentially saying these bacteria are doing something that's called quantum search. So in quantum computation, there's a particular kind of quantum algorithm for quantum computers. In fact, I was on the experiment that first demonstrated this, assuming the bacteria are not doing this, by the way, that where you can find your way from point A to point B in a way that is mysteriously faster by having waves that try to find their way and that interfere positively at point A. So they start at point A, and they interfere positively at point B, and so they make their way faster than they could. Now, we were actually able to eliminate this pretty rapidly, that it was this particular kind of algorithm. But we figured out that, in fact, what's going on is another kind of algorithm which relies on this ability of quantum particles to be in 2 places or 3 places or 8 places or a gajillion places at once. Again, a gajillion is a technical term, right? So what's happening is that this particle of excitation, this exciton, is not following just one path through this photocomplex. It's actually, in its weird quantum way, following multiple paths at the same time. And where it ends up comes from this interference between the wave of this exciton as it's in 2 places at once, and so it moves around and it gets, in this funny quantum mechanical way, it can go more efficiently through this complex than it could if it were just some dumb classical thing.
All right, so here comes dumb classical.
That's a moron, right?
So, a moron, right? Just don't be a boron, okay? All right, so what's happening is the exciton enters a forest of chlorophyll molecules, all right? And instead of following some path that's determined specifically like the force it has when it enters and the force that it has when it exits, it's actually maybe taking all of the possible paths, and when it gets to the end, what's represented there is that probability of the path that it took. So there was a probability that it would take any given path. It only took one, but you'd only know that when you get to the end. So this is one of those probability, God throws dice kinds of things in quantum mechanics.
Right, it's like that. And this allows it to get from here to there without losing energy. I mean, the ordinary way that if you were like I'm a professor of mechanical engineering at MIT, and if I were to give this to my students and say, we want this thing to get from here to there, we'll make this point at lower energy, and this exciton will just bounce down the hill and get down there because it's going to go downhill. But the problem with that is it's losing energy. And what you would really like is to have the energy here and the energy there be basically the same. And it's by taking these different paths simultaneously, it can go through a process that allows it to search through the space and get there in a way that's efficient without losing energy.
Are you buying this, Paul?
Yep. No, for me, it was that's how I got interested in the subject as well. It seemed, well, I was interested in the possibility of quantum biology many years ago, but this was the first definitive set of experiments that really did seem to put the subject on the map. So
now,
I think it's the best we've got.
Did the experiment say that's what it's doing, or did the experiment say it couldn't possibly be doing anything else?
Oh, there's always let-outs. Of course, in science, this is always the case. To absolutely 100% say it's got to be quantum mechanical, don't think we're quite there yet. But there are certainly some aspects of the experimental work which are strongly suggestive, as Seth was saying. You can zap these things with lasers and sort of mess up the process or enhance the process. Putting it all together, I think the case is pretty plausible. But it's not 100% certain that there isn't some other funny going on.
And we should say it's also not 100% certain on the quantum relationship to bird migration either, right?
I mean, are we allowed to disagree now? I mean, we've been so harmonious here. It's like this New York.
All right, let's
disagreement?
Yeah.
Get some excitons going here?
That's right.
I think,
as George W. Bush said, bring it on. Right?
There we go. That's right, yeah, if you're not with me. Yeah. So the difference, I think, is, so there is very good evidence that you have quantum mechanical effects in the photosynthetic system. That's the very best, that's the beautiful measurements. The question, however, what's not so clear, where I disagree a little bit is, does it matter? Because if you were to do this classical, boring way, the moron, and going through, you might actually get very similar efficiencies. If you do these calculations, it's not very clear that you actually gain all that much. Or in particular, where you gain something is in the very beginning of photosynthesis, which is very fast, which is, where you don't lose a lot of energy because it is so fast. And then there are other steps where you lose more energy later down the stream, and it's much less clear, what you gain from that. So it's more like maybe you make a very fast step a little bit faster, but that doesn't gain you a lot of efficiency. That raises from 99.2% to 99.2001%. The question is, does it matter for nature? And that's not so clear in the photosynthetic system, really.
Can we explore, before Seth answers that, just so I can get clear, how does the photosynthetic sort of screening mechanism or efficiency mechanism compare to the cryptochrome mechanism that you've seen in birds? Here we have two molecules that have some sort of quantum potential here, acting in similar ways, different ways, radically different ways? How would you?
I think it's much faster in photosynthesis. So that's where we're talking about these timescales of femtoseconds, picoseconds. In order for that bird mechanism to work, and there it's much less clear whether there's a quantum effect. But if it were there, it is clear that it's biologically significant. There we need timescales of maybe microseconds. So we're talking about 1,000, maybe a million times longer. And it's much less obvious how you can get quantum effects on that scale. It's always, what helps you to get quantum effects is you make it small, you make it fast. So whenever you can create something like that, that helps you. And that's what you have in photosynthesis. So there's really not a lot of mystery that you have quantum effects in the first 100 femtoseconds. And maybe there is not even a way to avoid them, because it just happens whenever you deal with atoms on those timescales. The question is, has nature really used that in some clever way, or is it just something that happens to be there?
Go get him, Seth.
Yeah. Thorsten, you're wrong. No, no, I actually must disagree with your disagreement, because, and to bring this up to say why I think that quantum mechanics is quite important in this transfer process, let's talk about tunneling again. So tunneling is a phenomenon where you go from point A to point B through something that you shouldn't be able to get through at all, okay? Now, if you were to make classical kinds of models of going from one chlorophyll, of this exciton hopping from one chlorophyll molecule to another chlorophyll molecule, the kinds that were made back in starting in the 1930s, and you ask, what are the rates? In these classical kinds of models, what happens is you don't have tunneling, you just get a little tiny probability of hopping over this barrier and moving to this other point. Now, these classical models cannot explain the speed with which these excitons hop from chlorophyll to chlorophyll. And in fact, you need to have something that is highly coherent, that is to say, tunneling, that allows the exciton to go from this point to that point. Now, it's a feature of quantum mechanics that actually at this microscopic scale, these kinds of tunneling phenomena are intrinsically much faster than these things that are just like, oh, hopping over that barrier. So, in fact, the coherence of this process, which is, as you say, has been demonstrated on the scale of hundreds of femtoseconds, which is a very short time, right? That actually is very important for the actual speed with which this exciton gets, from one chlorophyll molecule to another chlorophyll molecule. So that's a place where I think that the experiments, and the experiments strongly demonstrate this. What the experiments do is you zap this, you zap this photocomplex with light, you create this exciton here, and then a few tens of femtoseconds or 100 femtoseconds later, you zap it again. And what you can see is, what the experiments show clearly are these oscillations from this quantum mechanical tunneling, which is a sure sign of tunneling. I mean, it's not as sure as death, taxes, and maybe the second law of thermodynamics, but it's still pretty darn sure.
Could I just throw in another general point? Because we know tunneling is important in organic molecules, because my university, at Arizona State University, we do experiments directly measuring electron tunneling through organic molecules. For example, as a method of fast sequencing of DNA. There's a differential tunneling rate through the 4 nucleotides. So this is now technology exploiting tunneling in organic molecules. So we know it must play a role.
Let's explain the tunneling a little bit. Is the tunneling a feature of the quantum landscape? Is it a property that's being exploited by the biological system to maintain this coherence? Because as we've said at the very beginning, if you don't have coherence, you can't take advantage of the quantum mechanical phenomena. In the case of photosynthesis, the tunnel is your energy-free chute, and the classical model is your energy-consuming ladder. Is that what we're talking about with tunneling?
Yeah, so actually tunneling, if you have an energy ladder, tunneling is suppressed. So if you have energy differences, then in fact, this kind of wave-like nature of quantum mechanics doesn't like it. The way that tunneling works is you have this point A and this point B, and this big barrier you're not supposed to be able to get through in between. And it's not like the particle suddenly like hops from there. The wave for the particle starts out over here, and then a bit of the wave leaks in over here. Halfway in between, the particle is in both places at once, in its inimitable yet counterintuitive quantum mechanical way, and then the wave ends up all the way over here. And that can only happen if the energies are the same. So having no energy landscape is important for this tunneling to take place.
All right, Thorsten, let me come to your defense here for a moment. He said at a certain point, Seth, that much greater energy efficiencies come from the tunneling phenomenon that he says there have been experimental observations to. What is the much greater energy efficiencies? You suggested it might be, you know, a 0.1.
It depends on what it is that loses your energy. What is the time scale of that? Do you lose energy on picosecond time scales? Do you lose energy on femtosecond time scales? Then these effects, you know, matter a lot. But if you lose energy, let's say, only in an hour, then you probably don't care, you know, which way it's going, because even that incoherent hopping, this classical mechanism would be fast enough that you don't lose anything. The other problem, if that time is very long, is that in that mechanism that he described, there is nothing that prevents the energy from going back where it started from. You don't have the directionality. So unless you have these times very well matched, and in photosynthesis, it looks like that the loss rate is about 1,000 times longer than these processing rates. So you have a lot of time. And that's why it's a little bit difficult to say. And I think that if you look at that, yes, for this very first step, it gets faster, but then you compare it to something that's 1,000 times slower, and so in the end, you don't gain a lot of energy. Now, having said that, if you're a bacterium that is starving for sunlight, you know, even 0.5% more can give you an evolutionary advantage, and it may have made a difference.
So part of our difficulty here is we don't necessarily have the tests to understand what efficiencies are absolutely relevant to the biological system and what efficiencies just look good on paper as a mechanical engineer.
Well, there are experiments about this. If you alter you take these green bacteria, and they have a thing called a chlorosome, which is 400,000 or so chromophores, chlorophylls, all wrapped up in these big cylinders. And there it's actually thought that these quantum mechanical effects are strongly pronounced because there's very strong, the tunneling rate is very rapid between these chlorophyll molecules. Now there, if you actually alter the way that they're connected to each other genetically, and you look over time, you find that after like 30 generations or so, because over 30 generations, a 5% advantage will mean you're the king of the hill. So the bacteria then revert to their wild type if you mess up their interactions a slight amount. So there does seem to be some strong advantage in the architecture, the way that it's found in nature.
Even at the incremental energy levels that you're talking about there.
Yeah.
Over time, if you do the full calculation over time and generations and taking the genetic considerations, it's a very important thing. And of course, we are talking, as you said at the beginning, about a couple of billion years of life emerging.
Oh, more than that, yeah.
Now let me throw in another quick monkey wrench. I mean, we're all talking about that efficiency is what nature tries to achieve. We don't know that. Although we're biological organisms, we don't know what the photosynthetic system is trying to do.
Well, if you look at humans, efficiency doesn't necessarily seem to be the goal with humans.
Yeah, right. But it also could mean that you protect yourself from damage. You know, maybe it's actually a bad thing that the light levels change over the course of the day by many orders of magnitude. So if you're running at top efficiency, maybe you burn through in the noonday sun. And maybe what nature has to do is make sure that does not happen. And so there are lots of things that's actually, in my mind, the biggest problem and maybe sort of an avenue forward. before we maybe answer whether quantum mechanics is, what makes life different from inanimate matter, maybe there's certain functions that we can describe where quantum mechanics really helps. There's certain transport processes that, quantum mechanically you can handle differently. Maybe there are protective processes that quantum mechanics can help. And maybe once we start to have an arsenal of these different functionalities where quantum mechanics plays a role, we will find that in nature. And we may not explain life yet, but we're sort of halfway in between where we are now and that.
Actually, that has been found. In fact, it brings up another analog with quantum mechanics. There's a kind of, in quantum computing, there's something called quantum coding theory, where you protect your information from this decohering environment by storing information in states that have certain kinds of symmetries, like these entangled states we were talking about before. So now, as you were saying, I mean, actually, I don't really think you're wrong. I was just disagreeing with you just for fun, but in photosynthetic organisms, protecting yourself from light is a big thing. There are some photosynthetic bacteria that don't even start photosynthesizing until like 4 o'clock in the afternoon, because before then, well, it's just, too darn hot.
Happy hour.
Right, exactly. But when the leaves turn color in the fall, what you're seeing is that the green chlorophyll molecules are being reabsorbed because they're useful and they can be used later on. And you're left with these beautiful orange colors in maple trees, for instance. And those orange colors are from keratin molecules. Keratin molecules, one of their main purposes is to do sunblock, is to do photoprotection. And the way they do it is based on entanglement. Because what happens is there are bad excitons, and bad excitons are entangled excitons where the electron and hole have their spins correlated like this, the so-called triplet states. Whereas good excitons are the kind that get created in the processes that you're talking about, where the electrons and holes are always opposite, so-called singlet states. Now, these triplet states are bad because they create oxygen that can waste things, and they also gum up the works. They're just bad all around. Like, they basically give the photosynthetic organisms a wicked sunburn. So what the keratins do is that they select the excitons by their state of entanglement and suck up and vacuum out the bad triplet excitons. So this is, in some sense, just a kind of quantum coding theory. And all I can say is that thank God the bacteria and the plants didn't publish a billion years ago when they developed it, because otherwise my colleagues and I couldn't have published this in 1998.
A fear that certainly graduate students, pray every day to.
Yeah, it's bad enough being scooped by a competitor, but being scooped by a bacterium really
a couple
sucks.
of 100 million years ago. So, is this an example of quantum phenomena that can be tested in individual molecules like chlorophyll and keratin, and we don't quite understand how the plant is utilizing those, but they are always available for the plant, depending on the configuration of the molecules, keratin, chlorophyll, Paul?
Well, when you say always available, you mean...
These are easily testable phenomena. We can determine, just by looking at the keratin molecule, that it has a sensitivity to the orientation and the spin that Seth is talking about.
Right. The difficulty with all of these explanations is that you can't separate these the things we are interested in, a particular molecule, from its environment. It's it's embedded in its complex environment with all sorts of interactions going on, and we come right back to this problem of the complexity of life. That quantum mechanics deals best with simple things like electrons and photons and atoms and so on. And as you start getting more and more complex and start embedding things in a more and more complex environment, it's really hard to tease out the specific quantum properties of individual things. So you can pluck them out, and then you can experiment with them in isolation in the lab, but that's not the reality. And this is the real bugbear of doing biology, that you have to look at it holistically. It's a system.
So annoying.
And it's always hard to know. Cause and effect, it's hard to know what you can ignore and what you can rule out. Physics has made such incredible progress in the last 300 years because physicists are very good at knowing what to ignore. That ultimately we can say something sensible about the world without knowing everything about it. We can separate out little bits of the world and experiment with it. And that's why physics has been so good, because we know what to ignore, that there are different length scales and different size scales that are sort of decoupled. But in biology, it's all coupled up together, all the lengths and the sizes, and so everything's in there in a sort of mishmash. That makes it very hard for physicists to get to grips with it. And so what we're doing here is trying to understand, little bits and pieces of organisms. But really, it's a whole. It's a totality. It's a system.
And that, of course, is one of the huge challenges of science right now, is that as these fields converge, and we're just talking about one here, we could talk about neurobiology and information science if we wanted to. The challenge for scientists is to think heuristically, is to be able to imagine the system and develop experimental techniques that preserve the system, observe the phenomena that we want to observe, without having to constantly break things up into separate phenomena as the only way of determining causality. And this is one of the exciting examples of where you can be heuristic, system-wide, and begin to investigate some very small-scale effects like quantum mechanics.
And that's the important thing. You can't throw away the small-scale effects. Sometimes when you go up and describe a system holistically, you just average over things that happen. But if you take one of these carotene molecules that protects the system, you change one single hydrogen atom at the wrong place to a carbon atom, the whole organism will die because the protection is gone. So there needs to be a lot of mechanism to make sure that it is built exactly the right way. That is really important to, whereas for other things in a lipid, if that atom is at this place or another one, maybe nature doesn't care at all, or not that much, certainly. And so there's this difference, and maybe it's even at different times that nature cares more about one than the other. That 4 o'clock happy hour molecule may not care so much, And that's another challenge. Nature is actually rebuilding things all the time. When we want to build something, you want to have something that you put there and then you can study it for a year. Nature is completely happy to rebuild things on a scale of minutes and hours and completely reconfigure it as it needs. And we can't quite harness that mechanism to that same level yet, and that makes things difficult.
All right, so as I go here to my wave position and we think about concluding here, we've covered a lot of territory. It's been very, very exciting. And there's one thing that you mentioned, Paul, that I want you to explain before we get to the kind of final propositions here. And that is, you mentioned a moment ago, and we talked earlier about how biological systems have hijacked or found the opportunity to take a quantum phenomenon and use it for their advantage, bird migration being one, photosynthesis perhaps being another. You spoke about something a moment ago that's going on at Arizona State, which may in fact be another example of humans determining that they can use quantum mechanics to help in a particular sort of genetic molecular assembly process that uses tunneling to, and it's something you've patented. Can you describe this briefly?
Yeah, well, first, the work is due to my colleague Stuart Lindsay, and I've just been a sort of bystander and well-wisher. To describe what is now established technology, sequencing genomes, because big business, but the normal method of doing it is very cumbersome, very slow. Wouldn't it be good if you could just suck DNA through a little hole like spaghetti, draw it through, and then as each nucleotide goes through, read off what it is. How do you do that read off? Well, one way is to pass an electric current through it, and as we've been discussing, this involves the electron tunneling through the organic molecule, tunnels through the different, there are 4 different nucleotides, the 4-letter alphabet of life. Each one has a slightly different tunneling current, so you just sort of read it off on a meter, in effect, and that's rapid sequencing. And now he's trying to do this for proteins, protein sequencing from differential tunneling currents through the different amino acids.
So the quantum phenomena associated with tunneling, measuring the signature and determining the signature of each nucleotide would allow you to do fundamentally different and much more rapid genetic reassembly and recombinant.
Right. The hope is that this will become the standard technology in the future, yeah.
All right, so I love this. Where did life come from? Paul?
To say, you really mean how, I'm sure, because where, we don't know. It might have come from Mars, for example, and it's a
not a good
idea
example,
of mine.
Yeah.
But then what you're going to say is, well, how did it start on Mars? So we want to know, how did non-life turn into life? What was the sequence of events that led to the transition from just, a mixture of chemicals to a truly living thing? Now, the answer is, of course, we don't know. When I was a student, it was fashionable to suppose, which was many decades ago, fashionable to suppose that this process was so incredibly improbable that it would have happened only once in the universe, and we are it. Today, you can scarcely open a newspaper without seeing a distinguished scientist saying the universe is teeming with life. The transition from non-life to life is very easy, very straightforward. Well, in the intervening decades, we know we've discovered almost nothing more. So this is...
You know, which reminds me of when I was in school, there would be this, and they always used a British accent. They would say, the tidal pools millions and billions of years ago, lightning probably struck, then life emerged, you know.
Yes.
And it all sounded very convincing.
Right.
But
we haven't a clue.
it's malarkey. It's crap, yeah.
Right. We have no idea. And so the media give this very exaggerated notion that we're on the verge of discovering how non-life turned into life. We're very, very far from doing that. If you try and cook up life in the lab, you can make the first fundamental building blocks, but that's dead easy. There's no mystery about that.
Or you can do what Craig Venter does, basically make life from other life.
Right, you start at the other end, and he's already taking incredibly complex things. The problem is that even the simplest thing that we know, the simplest bacterium, is already so stupendously complex compared to this gunk that you can make in the lab, that bridging the two is completely unknown. Now, it could well be that there are sequences of events that actually are very probable. We just don't know what they are. Or it could be that it requires a sequence of chemical reactions or physical circumstances which are just so rare will have happened only once in the universe. We actually don't know whether it was something very likely or very unlikely. I've just got this hunch, well, it's a crazy theory, that maybe quantum mechanics played a role here, and I'll tell you what it is in a nutshell. That people think that life is about replicating things like molecules. You've got to make a copy of the molecule. It's the stuff that's got to be copied. But we understand that really life is more about information processing. Just have to copy the information. So if I take a file on a memory stick and put the memory stick in the computer and download the file, the computer doesn't make a copy of the memory stick, it just makes a copy of the pattern. It's just the information that gets copied. All you need to do biology is copy information. Information with variation and selection. So if we can find a system, it doesn't even have to be chemical, but copies information with slight variations, and there's a selection mechanism, the whole life game can begin. And that could be something as exotic as an interstellar grain spinning in a magnetic field. It might not even be chemical. So it's a really wild idea. But the point about quantum mechanics is that it's incredibly rapid, that things can happen quantum mechanically on femtosecond, picosecond timescales. Whereas great clunky molecules, I was talking earlier about 100 base pairs a second, that's incredibly slow. So life as we know it now is certainly not the most efficient and rapid means of copying information. So if we can find any system anywhere in the universe can copy information with variation and selection, we can begin to play the life game. And maybe organic life as we know it is some derived later secondary thing.
Thorsten Ritz?
Crazy.
Well, it's really tricky to answer the question if you don't really know what life is to start with, right? I mean, if you ask the question, how do you answer it? You have the old textbook answer of something that reproduces, that metabolizes, and so forth. Now maybe we're a bit more specific and say something that has these 300 amino acids, but these are just descriptive definitions. We don't know what the difference is, and that makes it extremely challenging to answer any of these questions. So the what is life? I think it's fascinating for me as a physicist who moved into biology that in physics you know what the big questions are. They've been around for a long time. In biology you ask these fundamental big questions, the first defining questions. Usually the answer is we don't know. We're still working on finding that out. We may quantum mechanically, we may not understand it fully, but we can describe it quantitatively very well. In terms of biology, we really, that's the fascinating thing. You just ask what it is, and the answer is we don't know. Go and research it.
At the risk of hearing another we don't know answer, Seth, can we use our understanding of quantum mechanics as a way of thinking about, at least, the emergence of consciousness?
You mentioned the C word.
You're just all about it.
Look, I just want to give a warning here. Look, this is the quantum mechanics is strange and mysterious, right? The origins of life are strange and mysterious. consciousness is strange and mysterious, and Donald Trump's hair is strange and mysterious, right? That doesn't mean that they're all the same thing or strange and mysterious in the same way. So I think one should be careful about, saying that all strange and mysterious things have the same origin. However, there is one place where we really do know, since you didn't want me to say we don't know, we do know that quantum mechanics plays a very important role in developing life, and that is in the introduction of variation. Because as Paul was saying, life, you can say proto-life is something that can reproduce itself, the information, with some kind of variation. Now, classical mechanics doesn't give you any mechanism for introducing variation. It's completely deterministic. Quantum mechanics, on the other hand, is probabilistic and can inject all kinds of information into the universe. In fact, the only explanation we have for why the universe is so varied and interesting, given that it came from an initial state, as Paul knows because I read this in his book about quantum mechanics on curved spacetime when I was a graduate student, the universe started out incredibly uniform, the quantum state was incredibly uniform, the laws of physics are simple. If that were a classical universe, it would have stayed simple. But because quantum mechanics is constantly injecting all kinds of, little fluctuations that become the seeds for galaxies, for the formation of galaxies, or for that matter, little mutations which become the seeds for cancer when an ultraviolet photon comes in and zaps one of your cells. This variation is being introduced by quantum mechanics. So one place where we know that quantum mechanics plays a key role, not just in the origins of life, but in the universe as a whole, is giving us this information and variation we see around us. And thank God for that, I say.
So enough predictability to sustain a process, the replication ability to sort of move it forward generation by generation, but the variation element, the indeterministic variation element, to keep things interesting. Those are the essential components of life itself, of consciousness itself. They are the unity of all the weird and wonderful things that go with all that is secure and stable about life. Guys, it's been a great conversation. Thanks so much to Paul Davies,
Thank you.
Thorsten Ritz, and Seth Lloyd. And I suspect we will be doing quantum biology in 10 years at the World Science Festival. And if you want to know more about quantum mechanics, see if you can squeeze into Brian Greene's program on quantum mechanics down at NYU. That's tomorrow night. It'll be the sweeping history of this fascinating anxiety called quantum mechanics in a way that only Brian can tell. For me, John Hockenberry, thanks so much. You've been a great host. Hottest ticket in town tonight.